So okay, that's it. Let's move on to the actual course. So okay, I'm going to talk about quantum field theories defined on the lattice, and in a school like this, it's always sort of difficult to decide, what kind of topics to include and what is going to be left out. Obviously, a lot is going to be left out. The idea is that I will try to focus on the basics, okay, and then give you, if time permits, a couple of examples of contemporary problems in lattice field theory. Okay, so roughly speaking, the plan of the lecture is that today we're going to start with scalar field theory. Is this big enough? I mean, Silvia, you can see my writing? Good. So today we're going to talk about scalar field theory. So we're going to discuss the basic ideas that underlie the lattice formulation of quantum field theory in the simplest possible case. And then, sticking to scalar field theory, we're going to discuss issues related to the sort of renormalization, so from a sort of renormalization group point of view. So we're going to try to understand how to relate results that you get by defining a quantum field theory on the lattice to theories in the continuum, which is what we're interested in at the end of the day. And then we're going to sort of start introducing a little bit of complexity into the game. So we're going to talk about fermions. And then finally, we're going to talk about gauge fields. And at this point, we will have all the ingredients to actually discuss QCD. And I would like to have some time at the end actually to discuss a few applications of lattice field theory to models beyond the standard model. Okay? And then the final argument will be the determination of alpha strong as an example of a sort of contemporary application of lattice QCD. We'll come back to this at the end, but I think I'd like to say from the very beginning that this is a very important result for our phenomenology. Okay, we're going to have another 20 plus years of physics at the LHC, and given that there is no direct evidence of new physics, the LHC program is going to be mostly a program of precision physics, okay? And therefore, the precise determination of standard model quantities has become a central sort of topic for, well, pretty much for the entire community, and in particular, the determination of alpha S is of great importance, okay? And I will try to argue that lattice field theory is a prime tool to actually determine alpha S, but that's for the end. Okay. So today is going to be all about scalars. Okay. So scalar field theory. Again, I'm not sure about how much you have already seen. I'm going to start from the very beginning, and we're going to have coffee breaks. We're going to have lots of opportunities to chat. If you think that what I'm saying is completely trivial, just let me know, and we can speed up a little bit. Okay. So the sort of starting point will be the path integral formulation of quantum field theory. So in general, I'm going to be interested in quantum field theories that are defined by a path integral, so by a generating functional, which is an integral over all sort of field configurations. the exponential of I times the action plus source terms. Okay? So the source term, this j dot phi, is simply the integral. I'm going to assume that we are in d dimensions. I'm going to keep d arbitrary except when d is going to be equal to 4, and maybe a few examples when d is going to be equal to 3. But at least at the beginning, I want to keep the number of dimensions as an arbitrary parameter. Okay? So this is the source term. And, part of what we're going to do is that we're going to give a precise definition of what this path integral actually means. Okay, we're going to, especially when we define the theory and the lattice, we're going to have a very precise definition of what the integration measure is and how to compute the generating functional. But in general, given the generating functional, you can compute any correlator of fields. Okay, and if you're interested in our own sort of world, we're going to be interested in a theory which is defined in a continuum space-time with a Minkowski metric. Okay, so this is all. So at this stage, I'm really talking about a continuum theory defined in Minkowski space, and then field correlators can be computed just by taking functional derivatives of the generating functional. Z of j, everything j equals 0. Okay, so if you're able, in one way or another, to compute the generating functional, you have access to all the field correlators. Okay, and these sometimes go under the name of Whiteman functions. They satisfy a number of sort of fundamental properties that we're not going to discuss in detail here. We would need a dedicated course for that. But the important feature is that once you know the correlators in a quantum field theory, you can actually reconstruct the full theory, okay? Which means that the knowledge of the Whiteman functions gives you access of the entire sort of quantum field theory. So it allows you to reconstruct the Hilbert space of physical state, and it allows you to compute physical quantities that you may be interested in. Is that okay? Sounds familiar? Yeah? Okay, very good. So the first step that we're going to take is that we're going to move away from Minkowski space-time. Okay, so we're going to do a Wick rotation, and we're going to move to Euclidean space. So everything that I'm going to discuss is going to be in Euclidean space. So I'm going to define an imaginary time, which I'm going to denote by, I should call this xd, not x4, which I'm going to denote by xd, which is minus I x naught. Okay, so in Minkowski space, my space-time indices go from 0 to d minus 1, and in Euclidean space, my indices will go from 1 up to d. Okay? And I will try to stick to this convention consistently, hopefully. Okay? So once you rotate to Euclidean space, you can actually define the entire field theory in Euclidean space. So we can define a Euclidean path integral in exactly the same way. And the only result of the Wick rotation is that now this exponential of IS that appears in the usual path integral is replaced by an exponential of minus S E of phi, where this is the Euclidean action, plus, again, the source term. Okay. And at this stage, you already see the close connection between the path integral formulation and statistical mechanics. Right? This really looks like a partition function, statistical mechanics partition function, where this exponential of minus S is your Boltzmann weight. Okay? So very soon I will get rid of the E. Okay, everything is going to be Euclidean, so hopefully I will not write E explicitly, but hopefully there will be no confusion. Okay? And the Whiteman functions are going to be recovered by analytical continuation. So we're going to compute Euclidean correlators. Okay, we're going to get correlators in Euclidean space by taking functional derivatives of this object here. These are sometimes called Schwinger functions. Okay? And if you want to go back to the correlators of your theory in Minkowski space, you simply evaluate the Schwinger functions at imaginary times. Okay? So that's in a nutshell the connection between the usual sort of Minkowski field theories and field theories defined in a Euclidean space. Okay? At this stage, everything is still in a continuum space-time. So the first step is to actually discretize the theory. Now, if you go back to the original paper by Ken Wilson that really started the entire field, I think that the suggestion by Wilson in that paper is to simply, discretize space-time. So instead of a continuum of space-time points, we end up with a discrete lattice of points. We substitute derivative with finite differences, and we see what happens. Okay? So that's exactly what we are going to do. Okay, so I want to call this, let's call this Euclidean theory on the lattice. We discretize space-time. I'm going to call little a the lattice spacing. Okay? We are going to replace derivatives with finite differences, and we're going to work out the consequences. Okay? And hopefully this is going to keep us busy for the next 5 lectures. Now you see, this looks sort of innocent, but it's actually an important change compared to the original continuum theory, in the sense that I have introduced a new scale into the problem. Okay? So this is the maximum resolution, if you like, in position space, which, when you go to momentum space, means that basically I have introduced a cutoff in momentum. Okay? So let's try to make this a little bit more precise. Okay? So the coordinates of my space-time points are going to be integer multiples of the fundamental lattice spacing. Okay? We're going to work in a box. So the total d-dimensional volume of the box I'm going to call omega, capital Omega, and typically it's going to be given by some size in the d dimension, which I'm going to call time extent, although you realize that in Euclidean spacetime this is purely conventional. Okay? There is nothing that distinguishes the d dimensions anymore, times a volume v, which I'm going to call spatial volume. Okay? And in some cases, in most of the cases that I'm going to be interested in, this is going to be a symmetric lattice, so all the dimensions will have a physical size L, and the total volume is just L to the D, and of course, ultimately, most of the time, we will be interested in the thermodynamical limit, where L goes to infinity. Okay? So these are all dimension-full quantities, right? So these are all centimeters or inches or Fermis. Okay? We will have sums over the space points. So I'm often going to use this symbol here, and this symbol will denote the sum over the discretized space-time multiplied by a dimensional factor of a to the d, okay? So that in the naive sort of continuum limit, the sum over x of f of x, when a goes to 0, will automatically give us the integral of the function. Okay? Everybody happy with that? Very good. And then, as I was mentioning earlier, when we go to momentum space, because we have discretized space, all the momenta will be inside the Brillouin zone. So the momenta will range from minus pi over a to pi over a. Okay. Right? So we have automatically a cutoff in momentum space as a consequence of having discretized the theory. And then our fields, phi, for a scalar theory, will be defined as usual on the sides of our lattice. Okay? So phi at x is just phi computed at some integer multiple of the lattice spacing, and we will alternate between this notation here, which is very close to the notation in the continuum, to a different notation where, again, we factor out the dimension of the field, okay, in units of a. Okay, so we will have a to the 2 minus d divided by 2 times something that I'm going to call phi with a subscript n. Okay? So this is something that looks very similar to the fields we use in the continuum. It has got mass dimension of d minus 2 divided by 2. This thing here is just a pure number. Okay? And I have, if you like, I've expressed the dimensionality of the field in units of this fundamental length that we introduced when we discretized. Okay? Right, so the other ingredient that we need is a discretized derivative, as I said before. So I'm going to introduce and now, of course, there is a lot of choice in how we discretize the derivative. So we're just going to take the simplest option. Okay, so I'm going to define delta mu of phi of x as 1 over a phi of x plus a mu. Okay, so this is the field computed at a position which is shifted by 1 unit in the mu direction minus phi of x. Okay, and again, you see immediately that when a goes to 0, this reduces to the usual derivative of phi. I'm going to use backward derivatives as well. Which are defined like that. Okay, and again, it's easy to convince yourselves that when a goes to 0, this actually tends to the same usual derivative. Okay, so this is a first example of something that is going to come back many, many times today and tomorrow, namely that there's a lot of choice, okay, in how you discretize things, in the sense that you can have different definitions on the lattice that will reduce to the expected sort of continuum quantity plus corrections that are suppressed by powers of A. Okay? So. And this is something that is going to come back many, many, many times in our discussion. Okay, with these ingredients, we're just going to write straight away the action. So let's consider a phi to the 4th theory. Okay. After what I've said, it shouldn't come as a surprise, okay, that I'm going to write the action in the following form. So this is, if you like, the naive discretization of the kinetic term, and then I'm going to add a mass term, and I'm going to add an interaction term. Okay? Is that what you would have written for the action? Yeah? Okay, so before we go any further, let's pause for a second and make a few comments. So first of all, you know, when you define in general, I mean, this is not specific to theories defined on a lattice. When you define a quantum field theory in a sort of path integral formulation, so when you define a quantum field theory by specifying the action tells you the field content of the theory. Okay, so in this case, a single real scalar field, and it also tells you the symmetries of the theory. Okay, So the symmetries of the action are the actual symmetries of the theory. Okay? So in choosing an action, okay, you want to make sure that the action encodes all the symmetries of the theory, right? And we will come back to this point in a moment, but you can already guess that in going from a continuum formulation to a discretized formulation, we have changed the symmetries of the theory. Okay? I will come back to this in a second. Before we do that, I'm going to rewrite these terms in a slightly different way, just to emphasize the connection to statistical mechanics. Okay? So if we switch to this notation here in terms of dimensionless quantity, we can rewrite these terms. And so, for instance, for the kinetic term, okay, I'm not going to. We get a factor of a to the d. We get a sum over n from this sum out here, and then we've got two derivatives. So 1 over 2, a factor of 1 over a squared, which comes from the derivatives. Then we've got two fields. So we get a factor of a to the 2 minus d. And then we get phi of n plus mu minus phi of n squared. Okay? So first of all, you see that the powers of a cancel. This is not unexpected. Okay? In natural units, where h bar is equal to 1, the action is dimensionless. So that's a good feature. We got that right. And so we can rewrite the kinetic term in this form. So we get a sum over n, and then 2d phi n squared minus 2 times the sum over mu. Let me write it like this, n plus mu. Okay. So this comes from squaring. So there is a contribution which is phi squared n plus mu, which is summed over all n and over all mu. This gives me a factor of d. There's another term which is exactly the same. Okay. Phi n squared summed over n. There is an implicit sum over mu here. Okay. So I get this factor of d, and then there is the cross term that gives me this. And here I've written explicitly the sum over mu, which was implicit in the equation above. Okay? And likewise, I mean, if you write down the mass term is just going to give you something that looks like sum over n m hat squared phi n squared, where again m hat is just the mass in units of the lattice spacing. Okay? And likewise, you will have a similar term for phi to the fourth. Okay. So why am I doing all this? The reason I'm doing all this is that if you put everything together, and I'm not going to do the algebra on the board, otherwise we'll spend the entire week on the action of the scalar field. But if you do the algebra, you can see that you can rewrite the action, and this is an exercise for you to do in your spare time, in the following form: some constant kappa that you have to determine times the sum over n and mu of phi n plus mu phi n plus lambda, which is another constant that you need to determine, times the sum over n of phi n squared minus 1 squared. Okay? And phi n is just a rescaled version. This curly phi is just a rescaled version of the original phi. Okay? I don't remember the rescaling on top of my head, but I think phi n is just phi n over kappa, something like that, squared. Okay? So, as an exercise, convince yourselves that this action here can be rewritten in the following form. Why is this interesting? Well, this is interesting because you see, this is really nothing but a statistical system with a nearest neighbor interaction. Okay? So, my Euclidean path integral is really the partition function of a statistical system. Okay? We can push the analogy even further in the case of the scalar field. What happens if I send lambda to infinity? Any idea? Remember that this sits in the Boltzmann weight. Okay? So if I send lambda to infinity, I get an exponential suppression of all the field configurations where this term is non-zero. Okay? So in the limit where lambda goes to infinity, the only configurations that contribute to the path integral are the configuration where phi squared is equal to 1. So this is really the Ising model. Okay? So this is all, just to give you an example, this is all to say that a quantum field theory defined on a discretized Euclidean space-time is nothing but a statistical system. Okay? Yes? That's something you have to find out as an exercise. Okay? So kappa and lambda are combinations of M and G. Okay? We could do it on the board, but then, then we really run out of time. Let's try to do something more interesting. But if you want, we can do it in the afternoon together. I mean, it's just algebra. Okay? But keep this in mind because this idea will sort of come back many times. Okay? Good. So again. Sticking to sort of very basic concepts, what is the relation between this sort of the partition function of a statistical system and a quantum theory of fields? Okay. Again, this is something which surely you have already seen, so I'm not going to derive this in great details, but basically the idea is that the path integral is a tool that gives you quantum amplitudes. Okay? So, a quantum theory is defined by a Hilbert space of physical states, which I'm going to call curly H, and an Hamiltonian capital H, which describes the dynamics. So in a quantum theory of fields, your dynamical variables, phis, are promoted to operators acting on H. Okay, so we get phi n as operators acting on curly H. We can then choose a basis for the Hilbert space, which is made of eigenstates of these phi's. Okay, so okay, and then this is okay. I'll put it up when I'm done. Okay, and then the path integral with boundary conditions phi and phi prime for your fields is just the matrix element of the time evolution operator between phi and phi prime, okay? Where u of t prime and t is e to the minus h t minus t prime. Okay, so our partition function, the partition function of the statistical system that we were talking about, with given boundary conditions, gives us the matrix elements of the time evolution operator between quantum states that are eigenstates of your field operators. Okay? So this is exactly the same as in quantum mechanics. Okay, if you've seen sort of a path integral formulation of quantum mechanics a la Feynman-Hibbs, this is exactly the same sort of type of argument, except that now we are in Euclidean space, and therefore instead of having a factor of I, here we have a factor of, well, we have just a minus. Okay. Is that familiar? Yeah? Okay. Good. So if we take a finite box and we choose periodic boundary conditions in time, in what I called the time direction, so we take periodic boundary conditions in time, so if it means that phi of n plus nd is equal to phi of n, then the partition function, when we set the sources equal to 0, can be written as the trace of the transfer matrix to the power n d. Okay, where the transfer matrix is just e to the minus h. Okay, and this is something that, again, we're going to use later. Okay, so again, remember, in this equation, on the left-hand side, we've got this quantity here, okay, computed with periodic boundary condition in the time direction. On the right-hand side, we have the trace. This is a trace in the Hilbert space of quantum states of an operator t, which is e to the minus h. So typically, t is positive definite, which is equivalent to say that your Hamiltonian is Hermitian. Okay? So if the Hamiltonian is Hermitian, the eigenvalues are real, and so e to the minus h is a positive definite operator. Okay? So this is not always guaranteed. Okay, so if you write a random sort of action, there is no guarantee that actually the path integral is going to lead to a well-defined transfer matrix, to a positive defined transfer matrix, and therefore to a properly defined Hamiltonian. So that's something that, in principle, you have to check. Okay? So for the case of the scalar theory, that's one of the problems in the problem sheets. If you want to try, I mean, you can derive explicitly this relation here, and you get an explicit expression for the transfer matrix. In everything that I will discuss, this will always be the case, and we will not sort of worry too much about checking this. But if one day you sit down and you decide to write some fantasy action and in order to define a quantum field theory, the first step should always be checking that the action that you define leads to a proper transfer matrix and therefore a proper quantum field theory. I mean, that there is a connection with the quantum field theory. Okay? Very good. I'm not sure how we're going to do this. Maybe we're going to have a break at some stage in the middle for 5 minutes, or what do you prefer? Or should I just get going until lunch, or until I'm exhausted? What do you prefer? You have to speak up at this point. I cannot answer that for you. I keep going? Okay, good. Very good. Right. So let's go back now to the action. I'm actually going to keep this. Okay? I'm going to keep this. I'm going to move on the board. And let's come back to the issue of symmetries. Okay? So as I said a moment ago, what the action does for you when you define a quantum field theory is that it specifies the degrees of freedom and it specifies the symmetries of the theory. So let's have a look at the lattice action that we defined, and let's try to discuss the symmetries. And what I want to focus upon are the space-time symmetries. Okay, so if you're in the continuum, you know, when we started this morning, we were talking about theories in Minkowski space. Is that the correct spelling of Minkowski? Okay, good. Then, you know, the symmetry is SO1 d minus 1, okay? And we rotated to Euclidean space. So we end up with OD. And now we go to the lattice. Let me draw our lattice again. And then you see, as soon as you discretize space, I'm just going to call it space because in a Euclidean theory, I mean, again, the distinction between space and time is gone. As soon as you discretize space, you break this OD invariance. Okay? And what is left is a symmetry under a finite group, which is the hypercubic group. Which I'm going to call H. Okay? So this is the group of rotations by pi over 2 and reflections. Okay? Now, when you get to finite groups, the notation is is a nightmare because of chemists. Okay, because the finite groups have been used by chemists for a very long time, and depending on which book you open, you find all sorts of different conventions, which I can never remember. So I'm just going to call this H. Okay, is the finite group of symmetries of d-dimensional discretized space. And if you want to think about H in very practical terms, it's basically the group that you obtain when you take together permutation of axes, okay, and reflections. So, in going from the continuum action to the discretized action, in this very sort of simple-minded way, so simply by introducing the lattice and taking finite differences, we've broken Lorentz invariance, or Poincaré invariance, down to a finite group. Okay? We still have a Z2 symmetry from sending phi into minus phi. And we have, let me write it here, a symmetry under discrete translations. Okay. So this is exactly the same as the Z2 symmetry that you have in the continuum action, and basically it will prevent odd terms in phi to appear in anything that we do. Discrete translation invariance is going to replace the usual translation invariance. The consequence of that, what is the consequence of translation invariance? Yeah, it's momentum conservation, very good. So the consequence of having only discrete translation invariance is that momentum is going to be conserved up to factors of 2 pi. Okay? We'll see that explicitly in a moment. Okay? So, having identified the symmetries of the lattice action, we can now think of how we classify states in a lattice, in a field theory which is defined on a lattice. And again, if you think about theories defined in the continuum, physical states are classified by the eigenvalues of the momentum operator. Okay? So they are classified by their momentum and by their properties under rotations. Okay? So basically they're classified by the irreducible representation, irreps, for irreducible representation of the little group of P. Okay, so this is the group of transformations that leave P mu invariant. So in the case of a continuum theory, the little group is O3, or if you include spinorial representations, it's the double cover of O3, which is SU2. Okay? And so physical states are classified by momentum and spin. Okay? What identifies the irreducible representations of SU2 is the spin of the particles. Now, when we go to a lattice theory, sorry, here I'm assuming that I'm in 4 dimensions, actually. We go to a lattice theory. O3 is substituted by the octahedral group, again, which is a finite group, and again, if you want to consider spinor representations as well, you have to go to the double cover of O, which is called, with a distinctive lack of imagination, 2O. Okay? And again, we don't want to get into a representation theory. I mean, again, if you're interested, these are things that you can find in books again. But there is something important that we need to emphasize here, right? So, in the continuum theory, the irreducible representations of SU2 are identified by half-integer numbers. Okay, so you can have arbitrarily high spins, 0, 1/2, 1, 3/2, up to infinity. Here, when we discretize space-time, the symmetry group is a finite group. Okay, so for finite groups, the number of irreducible representations is finite, and it's equal to the number of conjugacy classes in the group. Okay, so we only have a finite number of irreducible representations. Okay. Now, by the way, O obviously is a subgroup. I should say 2O is a subgroup of SU2. Okay. Anything that is a symmetry in the discretized theory is also a symmetry in the continuum theory, right? I mean, rotations by pi/2 are just a subset of all rotations. Okay? So, the irreducible representations of SU2 are no longer irreducible representations of O2 and can be decomposed into the irreducible representations of O2. So let me introduce just a little bit of notation. I'm going to call gamma J the irreducible representations of SU2. I'm going to call little gamma, again with some index K, the irreducible representations of 2O, okay? And then every representation of SU2 can be decomposed as the sum of some representations of 2O, like that. Okay? Again, you can work out character tables. You can find. There is an algorithmic way of doing this decomposition. It's not something we want to spend too much time discussing. I'm just going to give you the answer for sort of the lowest spin representation. So if we take the spin 0 representation of the continuum theory, this is actually equivalent to one of the irreducible representations of 2O, which is called A1. Okay? The details don't really matter. The spin 1/2 representation corresponds to G1. The spin 1 corresponds to something which is called T1. So the spin 3/2 again corresponds to just one irreducible representation of 2O, which is H, but obviously this has to stop at some stage because there are infinitely many irreducible representations here. There is only a finite number of them there. So for instance, when you go to spin 2, this is A plus T2, and so on. Okay. It's actually more interesting to do the opposite exercise, namely to focus on the irreducible representations of 2O and see where they appear in the decomposition of the irreducible representations of SU2. So for instance, A1 appears in the decomposition of J equals 0, 4, 6, 8, etc. A2 appears in a 3, 6, 7, and 9. I mean, these numbers are not particularly sort of meaningful, but I want to get to the stage where we can actually discuss a physical example. So the irreducible representation E appears in 2, 4, 5, and 6, and I need an 81, which appears in J equal 1. Oops. 1, 3, 4, 5, etc. And T2, which appears in J equal to 2, 3, 4, 5, etc. So why do I care about this? I care about this because when I look at physical states in a lattice field theory, they will be classified by these irreducible representations. Okay? And then if I want to connect these states to continuum states, that's the dictionary. Okay? So imagine that we perform a lattice simulation and we find a T1 state. Okay? So a state that transforms according to the T1 representation of 2O and nothing else. Okay? We find a state T1 in isolation. And as we go towards the continuum limit, whatever that means, we're going to discuss that in detail, but as we go towards the continuum limit, we still find this T1 state in isolation, then we know that we're looking at a J equal 1 state. Okay? However, if as we go to the continuum limit, we find that there are other states that come together, like say a T1, A2, and T2, okay? If we see that as we go towards the continuum limit, a T1, A2, and T2 states are coming together, then by looking at this list, you see that most likely we are looking at a state with J equal 3, okay? So this is the way we are going to, well, we are not going to, but this is the way physical states are identified in a lattice simulation. Right? So the states are all classified by irreducible representations of 2O, of the discrete symmetry group. And as we go to the continuum limits, we are going to see these states cluster according to what states are present in the continuum theory. Does that make sense? Okay. And this is a consequence of the fact that we broke Lorentz symmetry when we discretized. Okay? Lorentz symmetry is going to come back when we go to the continuum limit, and it's going to come back, and the way we're going to see that is that states that transform differently according to the irreducible representations of 2O will kind of cluster together in multiplets that correspond to the irreducible representation of SU2. I don't know what Ionivar is going to talk about, but he's been doing a lot of this. He's been doing a lot of reconstruction of excited states, where all the states are classified according to the irreducible representations of the discrete symmetry group, and then they nicely cluster into states that you can identify with confidence as continuum states. Okay? Right. So let's now start to get a little bit more, slightly more technical, and let's start by looking at the free theory and see what this free theory, this lattice field theory looks like in the free case. So again, we start from the Euclidean action, which is the action that you have up there with G equal to 0. You see, if you set G equal to 0, then the action is quadratic in the fields, and this is exactly the same as in the continuum theory. So we can write this as a sum over x and y, phi x, k x, y, phi y. Okay? It's a quadratic form in phi, and this kernel k, so let me call this as 0, k0, because it's the free action. This k0 we can write in the following form as a sum over z, as a sum over mu. And then we have one derivative. We have the other derivative. Like this, and then we have the mass term. Okay? Where these are just Kronecker deltas in the integer indices that correspond to these positions there. Okay? And again, we can always factor out all the dimensions in units of A, and this is an object which has got dimension of 2 plus d times a dimensionless quantity k0 mn, like that. Okay? Where this m and n are four-dimensional vectors of, d-dimensional vectors of integers. Okay? So x mu is a m mu, and y mu is a n mu. Okay, so using this notation and the dimensionless fields phi, we can rewrite the free action. Remember, this is a dimensionless quantity, so this is just the sum over n and m, and then I'm going to phi n k0 phi m and phi n. Okay, it's really just a quadratic. It's really just a quadratic form. Did I? Yeah, I want to keep the 1/2 here. Okay, and so we can now rewrite the path integral for the free theory in the following form. So z of j for the free theory and now you see I've done what I promised I would do at the beginning of the lecture. I've given you an explicit definition of the path integral. Okay? So especially if you are in a finite box, this is just a multidimensional ordinary integral. It's actually a Gaussian integral. It's a multidimensional Gaussian integral. Okay? And so we know how to compute multidimensional Gaussian integrals up to a proportionality factor, which is uninteresting. This is just the exponential of -1/2 Jm. Let me stick to the notation that I have in the notes. I'm going to call this delta 0. Okay? Where delta 0 is just the inverse of k. Okay. This is just the usual. It's just the usual Gaussian integral where you complete the square. You shift the integration variable, then you perform the Gaussian integral, which gives you a determinant of k, which is hidden into this proportionality constant, and this is what you get when you complete the square. Okay? Again, this is exactly the same calculation that you must have seen in the continuum case, except that here everything is very clearly sort of well-defined, right? You discretize space-time, you put it in a box. This is just a multidimensional Gaussian integral. Okay, this delta here is the propagator, just like in the continuum theory. Just like in the continuum theory, the way to find out the propagator is to go to momentum space. Okay? Before we do that, I mean, just a comment. You see, once we discretize, this kernel K is just a matrix, right? It's a very large matrix, but it's just a matrix. And actually, because of the deltas, because of the Kronecker deltas, most of the entries in that matrix are going to be zeros. Okay? It's an omega squared matrix, but the non-zero entries are just of order omega. Okay? This is what is called the sparse matrix. Which is not surprising, because at the end of the day, even in the continuum theory, this is a linear operator. Okay? So you take a linear operator, you discretize, well, you get just a matrix acting on a vector. Okay, so let's go to momentum space, and in order to find delta, so in momentum space, I'm going to define K0 in momentum space as the Fourier transform with respect to x and y of the position space quantity, like that. Okay. And again, we will not do the explicit calculation. Is again just a few lines of algebra. You take this expression and you plug it in here. Okay? You do a little bit of algebra, and what you get is the following. Is the following answer. So K0 of PQ is going to be the sum over Z of E to the minus I P plus Q times Z. And this is where all the Z dependence is. And then you get a sum over mu. We get e to the minus I. We have a over 2 p mu plus q mu, like that. I get a factor of 2i squared. And then we get a sine of a p mu over 2 and a sine of a q mu over 2, like that. And then we get plus m squared, like this. Okay? And somewhere here, there's a factor of a squared. Okay? So basically, this is the remnant of that term, this is the remnant of that term, and that's the rest. Okay? And we can rewrite this expression in a much more convenient form. I'm going to call this delta bar of p plus q. I'm going to tell you what delta bar is in a second. And then what is left can be written as the sum over mu of 4 over a squared times the sine squared of a p mu over 2 plus m squared. Okay. Basically, okay, let me tell you what delta is. So delta bar is this expression here, and this is exactly the momentum conservation up to factors of 2 pi that we mentioned earlier when we discussed the consequences of discrete translation invariance. So this is just a to the d times the sum over k from 0 to infinity of delta of ap plus aq plus k times 2 pi, like that. Okay? So you get momentum conservation up to factors of 2 pi, and then because p plus q has to be equal to 0 up to factors of 2 pi, you get minus sine squared. There is an I squared here that's going to cancel the minus, and you end up with this expression here. Somebody had a question, yes? Sorry. Say it again.
Make sense of indices in that expression?
Yes. What do you mean?
Like you have written k0 pq.
Yes.
So in the later part there is p mu plus q mu.
Yes.
So is it not compacted?
No. Okay, sorry. So these are 4 vectors.
Yeah.
Okay. This is p mu, q mu, and there is a sum over mu here, outside. Okay? By the way, this term disappears because of the delta function. Okay? It's summed over mu. I'm going to come to this now. So the next sentence, I think, is going to clarify what you're asking. Okay? These mu's are explicit, and they're summed over. Okay? So there is no, so on the left-hand side, there is no open index, right? I mean, all the indices are summed, but they're not contracted, if you like, as p mu. Okay? So you've got something which is mu dependent, something which is mu dependent, something which is mu dependent, and and the entire product is summed over mu. It's a very good question because it's exactly what I'm going to say next. Okay? So, right, so you see, this is nothing surprising, right? We've gone to momentum space. In momentum space, k is diagonal, okay, so it's proportional to a delta, and this is what it looks like, okay? So the inverse of k, so the propagator, delta, is just 1 over the quantity that is here in the square bracket. It's exactly the same calculation that you do in a continuum theory, except that the momentum conserving delta is replaced by momentum conservation up to factors of 2 pi. And this is a consequence of translation invariance, which is now only valid for discrete translations by an amount A. Okay? So this is our propagator. So now let's have a look at the, yes?
Is k a vector?
Which one, sorry?
K a vector.
K, where did it? No, K, okay, very good. Now, K here is just an integer. Just an integer.
So it's like you're adding vectors and scalars.
No, this is a, okay, yes, sorry. Yeah, no, it is a vector. So for every component, you have a K.
With positive integers.
Yeah. Yeah, actually. maybe like that. Okay, let me think about that. It doesn't make any difference. It's just conservation. So momentum in every direction is conserved up to factors of 2 pi. So now it is a vector in that sense. So yeah. So if you like, yeah, that's a better notation for all of them. Okay, so let's have a look at this term in the propagator. Okay, sine squared a p mu over 2 summed over mu. Okay, so let's look at this in the limit where a is small. Now, let's pause for a millisecond and let's try to think about what do I mean by a small. Okay, I've said several times that we're going to be interested in the limit where a goes to 0, where we remove the cutoff. But actually, you know, when we do physics, I mean, a goes to 0 doesn't really mean very much, right? So what is really meaningful here is the limit where a is small. Small compared to what? Yeah, exactly. Compared to whatever there is in the theory, which in this case is m or q or p, right? So let's go in a limit where AP is much smaller than 1. Okay? So what does that mean? Remember that the cutoff in momentum space is, let me write it just like that. The cutoff is of the order of a to the minus 1. So this means that P over A, that P is much smaller than 1 over A. Okay? So here we are in a regime, we are looking at a regime where the momenta are much smaller, are far away from the cutoff. Okay, this is an important concept that we're going to discuss a lot tomorrow, possibly on Wednesday if I keep going at this pace. Okay, so I don't want to talk about the limit where a goes to 0. I want to talk I will always be wanting to talk about the limit where a is small compared to the physics that I'm interested in. Okay, in this case, a is small compared to 1 over p, or sorry, p is small compared to 1 over a. Okay, so if we do that and we perform a Taylor expansion of this quantity here, we get 4 over a squared, and then we have the sum over mu, and then we get the first term, which is ap mu squared divided by 4, and then the next term is going to be a to the 4th, p mu to the 4th, divided in this case by 48, plus dot dot dot, where dot 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 really means terms that are of order a to the 6th. Okay? So maybe this starts to answer your question, right? So you see the lowest order term here is just p squared, where p squared is the usual p squared with the contracted indices, right? That's what you meant by contracted indices, exactly. Yeah. So here the index is explicit and it's summed over. Okay. The lowest term just gives you the sum over p mu squared. So that's the usual p squared with indices contracted. Okay. So we get p squared again. Not surprisingly, right? We expect in the free case that when we send the lattice spacing to 0, so when the lattice spacing is small compared to the physics that we're interested in, we recover the continuum result. And then let's have a look at the next term. Okay, the next term looks like a squared divided by 12, and then we have a sum over mu, and we have p mu to the power 4, and then we have other terms that are of order a to the 4th. So there are two things that we want to notice here. So first of all, the lowest order is just p squared, as we would expect. This term here is is O4 invariant. Okay? So at lowest order in an expansion in A, we recover Lorentz invariance, or its Euclidean counterpart. Okay? Then, for a scalar theory, you see that the first corrections are order A squared. Okay? And now, if you look at the structure of these corrections, this is a sum over mu, p mu to the fourth. Okay? So this is not invariant under O4. Okay? Again, this is not unexpected, because the lattice theory is not invariant under O4. This is invariant under H. Okay? This is invariant under the hypercubic group. But it's not invariant under O4. Okay? So we broke the symmetry. We pay a price, which we already see in the free theory. Okay? We have corrections that are, in this case, proportional to A squared that break the symmetry. Okay? Everybody happy with that? Now, remember, because the cutoff is A to the minus 1, okay, this term is 1 over lambda squared. Yes? Is 1 over the cutoff. And if Raphael was here last week, he must have spoken about effective field theories. Okay? See, this looks like a power-suppressed contribution. It doesn't look like it is. It's something which is power-suppressed by powers of the cutoff. If you think of a term in the action that would give rise to this kind of corrections, right? The term in the action would look like this. 1 over lambda squared, phi d mu to the power 4 phi. Okay? This is a dimension 6 operator, which comes suppressed by powers of 1 over lambda squared. Yeah? So the effect of the discretization is something that can be described in terms of higher dimension operators that are added to the action, suppressed by powers of the cutoff. This is something that we're going to discuss in much more detail in the next lecture. Okay? Yes? Yeah, if you have a continuum theory and you introduce a higher dimensional operator like that, you stick a cutoff, a sharp cutoff in momentum space. You add the dimension 6 operator, which comes suppressed by powers of 1 over lambda squared. You get exactly the same.
I could study this kind of term theory just by at least
Very good. Yeah. We will discuss this a little bit more later. But that's exactly the idea. In this regime, you can actually describe the entire lattice theory precisely in these terms. Okay? Now we're running out of time. The last item I want to discuss is the particle content. Okay? How do we understand? How do we describe the particle content of this discretized theory? So let's start, and let's see how far we can get. And this is one calculation that I want to do in some detail, because is going to be very useful when we come to discussing fermions. Okay? So let's try to discuss the particle content. Okay, again, as I told you before, okay, the physical states are going to be identified by the d-1 dimensional momentum, and then whatever other quantum number that is necessary. I mean, as we will see in the case of the scalar theory, there is only the energy actually that comes into play. Okay. So these states are eigenstates of momentum. Sorry. That. And there are eigenstates of the Hamiltonian. The eigenvalues of the momentum are identified by a d-1 dimensional vector, which I call P, and the energy is E of alpha. So every state is going to have some energy E of alpha. And now unitarity tells us that the sum over alpha times the integral over the spatial momenta. So you see, this is the sum over all states. Okay, states are classified by P and alpha. I'm summing over all alphas and all momenta of P alpha, P alpha. This is the projector on the physical state plus the vacuum plus the projector on the vacuum has to be equal to the identity. Okay, so if you take this equation here and you stick it in a 2-point correlator, okay, so you take this one and you insert it here, you can show that the 2-point function has a spectral representation which looks like that. Sum over alpha, the integral over P. No, sorry. Here I forgot the normalization of the states. Apologies. So this is divided by 2 P alpha of P. Okay. So I'm going to call this integration measure d-1 P over 2 pi to the d-1 times 1 over 2 E alpha. I'm going to call it d omega P. Alpha squared times an exponential of minus E alpha of P times X. Okay, let's work in 4 dimensions here, just for simplicity. I mean, it doesn't really change anything. Like that, okay? So this is a result which is always true. It's not something that has anything to do with the free theory. Okay? If you take any theory, the states are classified as eigenstates of momentum, energy, whatever other quantum numbers. The theory is unitary, so the sum of projectors over all the possible states is equal to 1. So if you take any 2-point function and you insert the identity, you get a spectral decomposition of this form. Okay? The only difference between what you may have seen in a sort of usual course in quantum field theory and this is this minus sign here instead of a factor of I, and this is again because we are in Euclidean space. Okay? So what we're going to do is that we are going to compute this correlator explicitly for the free theory. Okay? In the case of the free theory, we can actually compute this exactly. And then we're going to compare the expression that we get for this correlator to what we expect from the spectral representation, and that is going to give us the particle content. Does that make sense? Okay, very good. So let's do that, and let's try not to be late for lunch. So the calculation is done in full sort of detail in the notes, which I will leave behind. So I may skip some steps, but everything is in there. And like everything I do, it's all modulo typos and small mistakes and so on. So stay awake for another 10 minutes and check that what I say actually makes sense. Okay? Right. So let's compute. So we want to compute the two-point function, delta 0. This is phi x, phi of 0. And this is going to be the integral so it's the, if you like, it's the inverse of what we did here, right? We know the expression for delta 0 in momentum space, and so we're going to compute delta 0 in position space by inverse Fourier transform. Okay, so this is e to the I p dot x times delta 0 of p, and delta 0 of p is just 1 over that. Okay? So this is a d-dimensional or a 4-dimensional integral, which I'm going to split. So I'm going to split from the very beginning as the spatial part of the integration. Okay. E to the I p dot x. And the integral over the remaining time component. Okay, look, apologies. D and 4 are going to D is equal to 4. Okay, so there will be 4s and there will be D's in an almost random fashion. Let me call this dp4 over 2 pi e to the I p4 x4, and then delta 0 of t. Okay? So this quantity here, I'm going to call I of p and m. Okay? And this is what we're going to concentrate upon. Okay? We're going to do the integral over the time component of e to the I p4 x4 times delta 0 of p. And remember that in here we have a dependence on the spatial components of p, and we have a dependence on m. Okay? Which is why I wrote explicitly p and m there. Okay? Okay, good. So let's do that. So this I of p and m explicitly is the integral from minus pi over a to pi over a. Remember, we said from the very beginning that all momenta are in the Brillouin zone. Okay? Then we have dp4 over 2 pi. Then we get e to the I p4 x4. And now we can write explicitly the propagator. Plus m squared. Okay. Now this looks like a horrible integral, but actually it can be done exactly. So we're going to do that. So let me introduce a dimensionless quantity eta, which is just p4 in units of the lattice spacing, and then we can rewrite we can rewrite this integral as a. The integral now goes from minus pi to plus pi, d eta over 2 pi, and we have e to the I eta instead of p4, and then here I get I get n4. Okay, n4 is x4 divided by a. Okay, and now we're going to split the denominator into something that I'm going to call, let me see, well, we will have a part which has got eta, then we have 4 times the sum over the spatial components of sine squared a pk over 2 plus m squared a squared, like that. Okay? So in this sum, I've taken out I've isolated the term that depends on P4, and this is what is left. All the factors of A I've pulled out, okay, so that now everything that is inside the integral is dimensionless. Okay, so you get AP and MA, these are all, and eta, these are all dimensionless quantities, and the integral is from minus pi to pi. And now this is where I'm going to skip a few steps. I'm just going to write, you do a little bit of trigonometry, and you see that you can actually rewrite this as A times the integral over d eta over 2 pi from minus pi plus pi. We have e to the I eta and 4, and then 1 over, and what we get is 2b minus 2 cos eta. Okay, where b is what is left over from there. This is eta over 2. Okay? Very good. And you can find out what that is. Now the trick to do this integral is that I'm going to introduce a complex variable z, which is e to the I eta. Okay? And now, as eta goes from minus pi to pi, z goes around the unit circle in the complex plane. Okay? And so we can rewrite this integral here as minus a, then the integral over the unit circle of dz over 2 pi I. I mean, here all the factors need to be checked. Okay? And then we get z to the power n4, and then we get z squared minus 2 dz plus 1. Okay? And again, you have to take my word for this. There is a little bit of algebra in going from here to there. Okay? But now you see this is easy, right? Because so this is the integral in the complex z plane around the unit circle. So all we need to do is to find the poles of the integrand and use the residue theorem. Okay? So the poles are, it's a quadratic equation, so there are 2, and they are at b plus or minus b squared minus 1. Sorry. Okay? And again, if you look at at the details, you'll find out that only Z minus in this notation is inside the unit circle. Okay? Now this sounds very, very innocent, but when we come to fermion, we will get a completely different picture. Okay? And it will open a Pandora's box, actually, when it comes to fermions. But in this case, there is only one pole inside the unit circle, so everything is easy, so to speak. And so I'm just going to give you the answer in the interest of lunch, and I'll leave the lecture notes, and we can discuss it in the afternoon. I mean, there is nothing magic. Okay. So what we get is the following: is that when we put everything together, the two-point function looks like that. We get this integral over the spatial components, which I had factored out. Then we get this e to the I p dot x, which was also factored out. And then out of the residue theorem, we get something that looks like 1 over a times omega times x4 times 1 over 2 times the hyperbolic sign of omega, where omega is a function of p and m, obviously. And it's given by the log of b plus b squared minus 1 square root. Okay? So, again, just a couple of comments. First of all, so you see, if you compare this expression with this expression, you see that in the free theory, the states are simply, so there is no sum over alpha, okay? So the states are just labeled by the spatial momentum, the eigenstate of momentum, and they have an energy which is given by omega divided by A. So first of all, this is not obviously wrong because it has got the right dimensions, 1 over A. Okay, remember, omega is just the log of something, it's just a pure number. This B is something that comes out of massaging this expression here. Okay, so B is just a pure number, so this is just a pure number. 1 over A times omega is the energy of your states. Okay, so the particle content of the free theory is a set of states that are characterized by the three-dimensional momentum only, okay? And they have a dispersion relation, which is the one that is written over there. Okay? So E alpha of P is 1 over A times the log of B plus B squared minus 1. Now, what do we expect if everything has gone right? We expect that in the limit where the lattice spacing is small compared to the typical length scales in the problem, we recover the continuum theory. Okay? So when you get, when you do the algebra and you get an explicit expression for B, you can do an expansion. Okay? You can do an expansion for AM and APK much smaller than 1. Okay? And what you find is that at leading order, E of P, so I can get rid of the alpha because there is no alpha here, is just P squared plus L squared as you would expect, plus corrections. Okay? So, again, free theory. We can do the computation explicitly. We can look at the particle content, and we find that the particle content is just a scalar particle, no other quantum number. The state is completely identified by the spatial momentum, and the dispersion relation is a dispersion relation which is modified by the fact that we introduced a fundamental length scale in the problem, but at lowest order. So when you look at energies that are way below, that are decoupled, if you like, in a sort of in an effective field theory language, that are decoupled from the cutoff scale, it looks exactly as you would expect as a relativistic field theory. Okay? So this is a good place to stop. We're going to stop here and go for lunch. Any questions before we? Yeah. It's at the very beginning, right? So the Euclidean correlator gives you the time-ordered products of the Minkowski theory. Okay? So, the causality, like everything else, like locality, like the fact that things outside the light cone should commute, is all encoded in the Weitman functions. Okay? So when you rotate, you recover the time-ordered correlation functions of the Minkowski theory, and yes, so everything is there. This is a feature of the path integral, right? It's not something specific to the lattice. So the way to think about that is that you have your statistical. Remember, once you're on the lattice, you have a statistical system, right? I mean, who cares about causality in a sense? Then when you go to low energy, well, there is no in statistical mechanics. So then when you go to low energies, you recover the structure of the quantum field theory, and yes, all the properties are there. Okay? So, lunch.